Okay, so first we're gonna look at this photo by Miles Davis, and it's a picture taken from Traprain law, I think is how you pronounce it, at an elevation of 221 meters, and is looking towards Hopetoun Monument, and you can see these mountains in the background. The distance from Traprain law until the Hopetoun Mountain Monument, I used Google Earth, and I found it to be 8.28 kilometers. So here's how it looks in GeoGebra. I've plotted in the distances and the heights and the observer height. So I'll first look at the observer. This dotted line is, if you can imagine, like a leveled laser, a very powerful laser at the observer height, and that would be like straight ahead. Here we are at the monument, and we see that like these lines of sight are color coded, so that the blue line is the straight line from the observer to the top of the monument. This green line is straight line from the top of peak number 2 to the observer, and the red line is to peak number 3. And we see here that all, like the green and red line, are below the blue line, which is what the photo shows. So that's one thing. The other thing is, and we'll look at this a little bit more later, like this is a purely geometrical model right now, but if we're going to take into account refraction, we can use the approximation that refraction has the effect of flattening, quote unquote, the Earth. So that basically means that we have an Earth with a radius that is 7 divided by 6 times this radius here. So if we do that, we see that these lines to the distant peaks, and they get higher, or they appear to be higher, and we'll get back to these when we look at the peaks. So here we are at peak number 2, Ben Lomond, which is, in the picture you see that it's very close to the line here, and we see that it doesn't quite match in the geometrical model, but if we take into account refraction, we actually see that they are very close here. And here we are at peak number 3, Bainime, I don't know how you pronounce that. We see that it's a little bit below this line, but in this, with the pure geometrical version of this, it's quite a bit below. But again, if we employ the approximation for refraction, we see that this difference here is closer to what we actually see. So we see that the globe model with refraction matches reality. Okay, so here we are at the flat Earth model, and we'll just look at that real quick. Here we clearly see that the line of sight to the top of the distant mountains are clearly above the monument, which is of course what we don't see. And here we see total failure, if you will, on the flat Earth model. Like, the line of sight to the monument is down here, and the top of the second mountain, Ben Lomond, it's like, yeah, the difference is huge. And the same for the third mountain. We also see here perspective in practice, because this mountain is almost 50 meters higher, but because it's further away, it will look smaller to the observer. Anyway, the flat Earth model doesn't work. Okay, then we'll look at the second example. No surprises here, spoiler alert. Anyway, we have an observation from Traprain law. This time the observer height is 210 meters, and we're looking at this bridge here with these towers, which the top of the towers are also at 210 meters. I should mention, by the way, that Miles Davis seems very thorough in his observations and measurements, so I have no reason to doubt that, you know, the accuracy of it. Anyway, we see that these hills or mountains in the background are below or slightly above this line. And we'll look at that in the model. So here we have it. We picked out 3 spots, the bridge towers at a height of 210 meters, 46.1 kilometers from Traprain law. We have the second peak, Michael Bin, I don't know about the pronunciation there, at a height of 570 meters, and we have peak number 3, Earl's Seat, 101.6 kilometers away at 578 meters. Observer height is, as I said, mentioned, 210 meters. So let's see how this looks. Okay, so here we already see that this kind of matches the photograph. The green line is the peak number 2. Michael Bin here, which we see in the photo, is also above the line. And the red line is to Earl's Seat, which we see is, well, it's just maybe just a little bit under the line. We'll look at that later. So we see that this Michael Bin is slightly above the line to the towers, but we see that if we take into account, again, like we take into account refraction, we see that this actually matches reality a bit more. We see that this is, for an object being like 100 kilometers away, this is actually quite a bit. And we see that it matches more when we take into account refraction. And what about this last peak, Earl's Seat? We see that is quite, or relatively far below the line of the towers. So let's see what happens. Wow, it's actually almost in line. So this is the flat Earth version. So let's have a quick look. Again, we see that if the Earth was flat, the two mountains that we've used as an example definitely should be above the line that we see from the bridge towers. Again, we see even at this this far distance, there should be like a big portion of this mountain visible above the line of the towers. So once again, the flat Earth model doesn't really work.